Okay, common ion effect and buffers. Actually, here's part two. Finally, part two. Yes, I know. Oh, I had a hard time. I was trying to get the video yesterday. My clothes are different now, you see from this video, but oh well. Part two I had to do the next day. So 15.1, actually what I went over in the last video was 15.1, and there's not a specific assignment just on that one, but I want you to know how to do it. 15.2 buffers, this is the big one. And again, the worksheet, you do number 1, 2, 3, AB, and 4, AB. Now, to save time, and you'll know what I mean later with video and repetition and all that, for you and me, I would have to record a longer video, or you would have to watch another video, whatever. To save time, I'm going to show you some things in this video that are not going to be required yet. I'm sitting here looking for my chalk. I don't know where I put it, so it'll pop up in a minute. But I'm going to show you some stuff here that might be in the next video. So I don't know. I'll figure it out when I do the lessons. So maybe I'm teaching you part of the next lesson too right now, just because it'll save a little bit of time, and it'll make sense in the context. It's just a whole lot of information to do at one time, a whole lot of math stuff. Okay, so here we go. What in the world is meant by a buffer? Now, I'll just read in the notes here, 15.2, and I'm going to kind of skip through some stuff too here and there. A buffer equilibrium system is a specific equilibrium system which illustrates a common ion effect. Okay, it says this. Here's the way I think of it. A buffer system. Remember, a solution could be acidic. You know, if it's acidic, it means H plus or H3O plus is in excess, greater than the hydroxide. Well, let me back up a minute and remind you of something else. Remember that in water, pure water is not, all the molecules in a glass of water are not H2O. Some of them are H3O, well, we'll say H plus, and some are OH negative. They break apart. Okay? Now, the correct way to do that, the best way I've told you, was to put two water molecules. Because they collide with each other, one of these will break up into H and OH. And so you get H3O plus, and you have OH negative. The H plus will join onto the water, and then your OH is left over. So this is the best way to look at it. Now, here's the point. In pure water, H3O plus is equal to OH negative. It makes sense. For every H2O that breaks up, you know, if I want to put HOH or HOH, yeah, think about that. You get one H and one OH. The first equation tells you that. One H and one OH. It's just that in this equation, I have the H attaching to the water molecule, H3O. Okay, so if it's equal, it's a neutral solution. Neutralized, no problem. And we pretty much like neutral things. We like to drink water that's neutral. We don't want it to be, well, sometimes you want it to be acidic, like tea, or lemon, or what we say, lemon juice, lemonade, orange juice, anything like that, lemon or acidy. Okay, so now, when people talk about water that is alkaline water, alkaline means slightly basic, actually. Okay, so H plus, OH negative. If H plus is greater than if the acid is greater than the base, it's acidic, right? That makes sense. And if the other way around, if the base is greater than the acid, then it's basic. Now, it's not so bad if like I said, water is a little bit acidic, or if water is a little bit basic. But you definitely don't want to drink HCl, strong acid. You don't want to drink strong base. You don't even want to drink, you probably don't even want to drink 0.5 molar of H. That would be way, maybe not even 0.10, but I'll say for sure you don't want 0.5 molar HCl or 0.5 molar NaOH acid or base in you. So what this is pretty amazing, but a buffer is a chemical system that, how would you say this? It combats, it neutralizes the incoming acid or base. How about that? Now, here's the best example is actually in our blood. Isn't that amazing? You won't be able to understand it from what I'm going to show you here right now, this equation, but this system exists in your blood. It's called a blood buffer system. Now, what does that mean exactly? Well, what it tells us is you've got chemicals in your blood, and if I were to like, you wouldn't do this anyway, but if you were to put, just say if HCl were put into your blood stream, or if you ate it or whatever, if HCl, hydrochloric acid, strong acid, got into your blood, well then your blood, how do you neutralize an acid? You add base. Your blood has a chemical in it that is basic that will fight the acid and neutralize it. Okay? All right, what if you put a strong base into your blood system, an OH negative in your blood? That could be very dangerous for you. Your blood pH has to stay, did I write it down here? I didn't write it. Oh yeah, your blood pH has to stay about 7.4. Think about that. So that means it will be slightly basic. Your blood, 7.4. 7 is neutral. So if we put in an OH negative, it will be really basic. Well, then your blood has in it a component that is acidic that is going to shoot out, well, whatever, shoot out. It's going to neutralize the base. So acid comes in, so you have a buffer. If unexpected acid comes in, then the buffer is going to neutralize it with a base. A base is going to neutralize it, and it's gone. If unexpected OH negative is added in, then the buffer system gives an acid to it and neutralizes it. Isn't that cool? Now, that just naturally happens in a buffer system. So how does this work? I'm going to show you right here. So think about that now. So when you think, what is a buffer? It's able to neutralize acid or base that comes in. Now, how can you recognize a buffer? There are, let me see, are there two kinds of buffers? I'll just focus on two types of buffers right now. Think about this. You can have a weak acid system, a weak acid buffer, or you can have a weak base buffer. Now, a weak acid buffer is going to contain the weak acid. So actually, the first question I do is going to deal with this. It says acetic acid, CH3COOH. So let's write that down. I should have gone up a little bit higher there. We're doing 15.2. Weak acid buffer. All right, so first you start with the acid, CH3COOH, acetic acid. And you know how to do it with water. Yeah, I did it with water here. You know that it would react in the icebox, kind of equation like this. H3O plus. And I'm going to run out of space. CH3COO negative. I guess I can put it there for there, like that. All right, here's what happens. Real simple to remember this. This is very, very simple. I hope to see this. Think about an icebox. In a weak acid buffer, all right, well, let me do this. In a weak acid, all you would have in present is like, let's just say 0.100 molar of this. By the way, on this question, it's going to be 0.50 molar. So I'm going to go on and just kind of work out the problem that's going to be coming in a minute. We'll come back to it in a second. But, you know, if you only had a weak acid, you'd have 0.50 molar acetic acid, CH3COOH, and you'd have 0 of this and 0 of that. Okay, so then you got the X, and down here it'd be 0.50, and that would just be X, okay, minus X, whatever. Okay, you know how that works. All right, that is a weak acid. But guess what? A buffer is if you have, along with the acid, you have to have its conjugate base. So let's just say I've got 0.50 molar of that to begin with. So then down here, instead of X, it'd be 0.50 minus X. Notice this. If you have both acid, 0.50 present, and you have its conjugate base present, 0.50, it doesn't have to be equal. I could have 0.50 and 0.10, or 0.10 and 0.50. But if I have both this present at equilibrium, some acid, and its conjugate present, that is a buffer. Okay? All you need to do is you need to have a weak acid in a solution. Like, say in a solution you put vinegar, it's acetic acid, you pour it into a bottle, into a beaker. But then you have to also have some of the conjugate. Like, for example, sodium acetate. And I think that's going to be the one on the question. Is it? Yeah, it'll pop up on there. I'll show you in a minute. Okay, a weak base buffer is very similar. So again, I'll just take ammonia, because that's the most common one you're going to see. And in that ammonia system, you have ammonium and you have hydroxide. Okay, so if I only had ammonia and nothing, 0 of this, that would just be a weak base system. But if and down here it'd be 0.50 minus X, same deal. Okay, and then X and X. All right, and I didn't do the change there. Now, if I had, on the other hand, if I also put in, let's just say ammonium chloride, I added ammonium chloride into ammonia. So in other words, all I'm saying is initially I had some of this and this mixed together. So now down here it'll be 0.50 plus X. And by the way, that was a plus too. I wasn't paying attention when I wrote that down. But I'm not doing the math right now. I'm just showing you. The point is, if you have an acid at equilibrium, an acid and its conjugate both present, then actually you might look at the initials. But if you have these present, significantly present, then that would be a buffer. If I have both the base and its conjugate present, that is also going to be a buffer. All right, so that would tell you what a buffer is. All right, so before I do, I erased it. Oh well, I'll write it again. Before I do the math, though, I think I might want to talk about the equations. Where did I put those? Oh no, I actually put them on the next page. You know what? I think I'll do it on the next. Oh no. No, I better do it right now. It looks like I kind of went out of order. But if I skip the problem A and I go to the next page, how buffers work, I want to tell you how buffers work right now. But you don't have to read through all these notes. This is something that I don't know. Maybe in my notes I should have done this first, as I'm doing it right now, and not have the calculation yet. So let me go to the acetic acid one for a moment. So here's a system, CH3COOH, and I know I just did it again. I'm trying to save, not have time, and not have to keep doing this over and over again. I had it in the right place. I'm going to fit this on the chalkboard. Okay. There it is. Acetate is here. That's acetic acid. That's water. And that's hydronium acid. Okay. So in a buffer, you have some of this, and I just said I'm going to make it 0.50 and 0.50. You have both of these present. So how does a buffer work? All right. You need to know these equations, how to write this. It's going to be a stoichiometry equation. If let's just say this is a buffer. Now we already know it's a buffer. We have a weak acid buffer. Okay. System, weak acid buffer system. It contains both acetic acid, and it also contains acetate. Now why does that matter? If you add acid, strong acid. So let's just say we add strong acid into this system. What do acids neutralize with? What neutralizes an acid? A base. So if I add acid, like let's just say, for example, HCl. So I'm going to add HCl, and I'm going to add it into that system. I'm going to drop it into this container that has in it CH3COOH, and it has CH3COO negative. Actually, that's a good way to look at it. If I put some drops of HCl into here, I'm going to add it to this. Guess who's going to react with it? The base is. The conjugate base. Acid and acid won't react, but the base will. So HCl is going to react with the conjugate base in an acid system. In a weak acid buffer system, if acid comes in, then it's going to say, not the acid, but it's going to send the base, CH3COO negative, reacts with it. Now, I'm going to make a stoichiometry problem here. HCl plus acetate gives you what? It's going to give you two things. It's going to give you H plus is going to join on to that, and can you believe it? You're going to actually make CH3COOH. You're going to make some acetic acid. All right? And what will be left over? You'll have the Cl negative left over. Okay? Now, if I want to do my net ionic H, I don't really have to do that. I wouldn't need to do that here, but I'll do it anyway to show you. Because when you do a problem, when it says add acid to a buffer, all you care about is this equation right here, really. So that means that the CLs would just be they did not react. So just H plus joined on to CH3COO negative to make that. And yet, you could be asked on AP to write a net ionic equation where that happens. But if you're doing a calculation with a buffer, you're probably only going to need this equation. You'll see later. Okay, so if you add acid like HCl, that's what's going to happen. HCl, the conjugate base, the base will react with the acid. All right, and that's what you're going to get. Okay? On your worksheet, I wrote a general form. I don't know, this might confuse you. You might not want to see this, but call that HA plus, the CH3COO negative will give you CH3COOH plus A minus. So just whatever the anion is, it'll be like that. I guess that's the way I wrote. Well, whatever. I'll just remember that. It's easier. Okay, what's the other alternative in a buffer system? Well, what if you add a strong base? So again, I've got this container, and I've got in it acetic acid, but I also have in it some excess common ion, that's what we say of acetate. If I add a base, what's going to neutralize a base? Well, an acid. So which one of these two things in the system is the acid? And it would be CH3COOH. Yeah, so the acid there. This might be easier to figure out. So if NaOH is added into that system, the vinegar or the acetic acid is going to react with it. And it's just double replacement. Sodium goes to hydroxide. No, not hydroxide. I'm so sorry about that. Oh, what a bad thing that. The H goes, okay, I can't believe I said that. I'm so sorry. +1, -1. And then this is kind of weird the way I wrote this. +1 and -1 there. So sodium will go with by itself, actually. The OH goes with H+. This is a weird one because we wrote it backwards. So you're going to make water. I'm going to write this another way for you. And sodium will be left over. And acetate is left over as well. So sodium becomes a spectator ion, really. Well, I could have wrote the net ionic there too. But anyway, the main thing is OH and H+ neutralize to make water. Let me write this in another way for you. And yeah, I better write this another way for you. Okay, I want to show you another way you can write it. Remember, you can also write acetic acid like this. HC2H3O2. And almost every acid you write is going to be that way. H and then the anion. So this makes more sense. +1, -1, +1, -1. So sodium goes with acetate. Well, you can do that, but in reality what's going to happen is it'll be aqueous and dissolved, and H and OH go together. That looks a lot better, doesn't it? So if you add base to acetic acid, you're going to get water. The net ionic, I'll go on and put that too, just if you want a review on that, because we're right here. This, you never break up a weak acid. Okay? But on this side, you will break it up. Sodium acetate. And then water does not break up either. So what happens is only the sodium will be your spectator. Hydroxide reacts with the acetic acid, and it gives you those two things. All right, it gives you water is the main thing you get. The H comes off of this, HOH, and then acetate's left over. Okay, now, I know this might be kind of long. If you wanted to skip through it, you could, but I wanted to, let me show you what happens in a base system. I better do that as well. Okay, let's just say instead of having a weak acid buffer system, I'll leave that up there for now because I'm going to come back to it in a moment when we do a calculation. So let's just ignore that for a second. Let's just say now you have a weak base buffer. Now, the example I gave for that would be NH3, and you also have ammonium. So you have both the acid, the base, and its conjugate acid are both present. In the weak acid, you have the acid and its conjugate base present. Okay, so when I say present again, if I only had 0.50 molar NH3 and those were 0, this would only be a weak base system, not a buffer. But if I have any of this also, like I add some ammonium chloride, NH4Cl, into the ammonia, solution, like 0.50. I'll put 0.50 because 0.50 and 50, as you'll see later, that's the perfect buffer, is to have the equal amounts of both. But now this is a buffer system, okay, and it will be down here too, but I won't do the whole thing. So let's draw a little container like I did before. In a weak base buffer that I drew here, you have ammonia present, but you also have some ammonium. Now I know you have it in a significant amount. That's what I should say. And it came from another source. That's even better. So yeah, it's true that in an acid system, and only in an acid, if it were no buffer, you would have some of this present, but a very small amount. But if you had some of this present because it came from another source, like you added sodium acetate to this, now it's a buffer. If I add ammonium chloride to ammonia, now it's a buffer. Okay, so this came from an outside source. That's how you know a buffer. Okay, so what are the two possible reactions here? If I add acid to a base system, okay, think about the things that are here present. Which one of these reacts with an acid? How do you neutralize an acid? You react it with the base. The base, you throw the base at it. The base is which one? NH3. So if I add acid like HCl, then the base comes to it, NH3. And now look at what they make. This particular reaction will make NH. You can actually just write NH4Cl. HCl plus NH3, it's like a Lewis reaction. But now, if you do a net ionic, what's going to happen is you don't break up the ammonia, but you will break up this ammonium and chloride. And so the chlorides can come out. So really this tells you what's happening. You add acid, it attaches to ammonia and makes ammonium. Okay? Weak bases receive the proton. So anyway, instead of having, notice that what happens though, instead of having the strong acid, now you only have this weak conjugate acid resulting. So you add acid, then if you add acid to this system, then the more basic one, well, the base of these two, will react with it. There it is. And then the last one, if I add base, so add acid, I made HCl. For base, I'll make it NaOH again. If I add base to this system, what do you need to neutralize a base? You need to add acid to it. Which one is acid? The NH3 or the NH4 plus? That's your base, that's your conjugate acid. So the conjugate will react with it. The acid is the conjugate in the weak base buffer system. So NaOH is going to react with NH4 plus, and kind of like I showed you before, think about this. The OH negative is going to react with an H plus to make water. Okay, so I'm going to take one of these H's away to make water. And then what are you left with? You take an H away, you're left with NH3. And you're also left with the Na that we didn't do anything with, Na plus. So you add sodium hydroxide, and the ammonium reacts with it. Ammonium acts as an acid. Maybe it would help you to know that that's the acid, the conjugate, and that's the base. And so what does an acid do? It donates its H to the base. So it can give the H to OH to make HOH, right? The H plus came from ammonium, and the OH came from OH, sodium hydroxide. Okay, and then NH3 was left over. You take away an H, and now you have NH3, the conjugate base of this acid, and now you have sodium left over that was unreacted. If I did the net ionic of this one, I'll just do it real quick too, because again, it could pop up on the equations. Na and OH. Again, you don't break up NH4 plus, or water, or ammonia. And then you have sodium here. So it looks like which things repeat? Na plus, Na plus. So hydroxide and ammonium give you water and ammonia. That kind of makes sense there. All right, there it is. Wow, I know it's a lot of information. I'm starting to think that what I'm teaching you right now, you'll see, this might be enough to do the next two assignments just about. We'll check. I'm going to show you a lot of info. So everything I've shown you is how the equations go. So if you have any buffer system, it's a weak acid, I wasn't going to erase it, but oh well. It's okay. Let's just do it that way. All right, let me go back now. Now comes the math. All right, now back to 15.2, and we'll go to this problem A, and this makes more sense. I don't know. Okay, it says this. Okay, here is well, I'll tell you a little bit more good news about this in a minute, hopefully. All right, let's start over with the math. A. Acetic acid ionizes in water according to the equation above. A solution of 0.50 molar acetic acid was prepared for an experiment. And I don't know how many times I'm going to write this down in this video. Next, solid sodium acetate was dissolved in the solution. So we added some solid sodium acetate. Okay, and to make the solution 0.50 molar sodium acetate. Number 1, calculate the pH of this buffered solution that is 0.50 molar CH3COOH and 0.50 molar sodium acetate. Okay, this is going to be easy. After all that I just told you, this part is going to be easy. Icebox. So you have a weak acid system. Now, remember I told you one thing about all equilibrium I always tell everybody to do, whatever kind of equilibrium you're doing, I always recommend you make an icebox. You can always abandon it later and say, hey, I don't need the icebox, and I'm going to probably do that kind of in this problem for you. All right, so in this reaction, let me see, I'm going to, oh, you know what? Oh, my goodness. I am going to have to, make a third part of this video. I talked so long, and I got something else I have to do right now. Well, I'll come right back to this soon. I hope. Or will it be next time? We'll see. If I've got time to get it today. Before I do the math, yeah, I better hold back on that. So, all right. I showed you a lot anyway right there with the equations. Actually, you can already do, I think, number 1 and number 2? Well, somewhere in the homework that will come up. I'll check back. I'll get that to you.